Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 8 on algebraic thinking. And today we're talking about Section 8.3 on functions. In this section, you'll be able to understand and explain the concept of a function, including domain and range, different representations of functions, and the derivation of the formulas for the sum of n terms of arithmetic and geometric sequences. You can think of a function as a rule where when one value is given, the function or rule specifies a resulting value. So in this example, a student calls out a number and the teacher calls out a number as an answer to the student's number. And they want us to guess the teacher's rule for these responses. So in the first case, when a student says 1, the teacher says 3. When student says 0, the teacher says 0, et cetera, et cetera. And then maybe later in the day or the next day, it looks like this. So what you want to do is try to find a pattern to these responses. And I'd say in this example especially, the pattern is pretty clear. If you compare the teacher's answer to the number that the student called out, notice that the teacher's number is always 3 times the number given by the student. And so in this case, the rule is to multiply the given number n by 3, which means if the student gives the number n, the teacher is going to give the number 3n. This one is a little bit more complicated maybe. I notice, for example, that all these numbers are odd. It's kind of difficult to see the pattern. For one thing, you know, these numbers over here given by the students skip around. If they had given us maybe 2, 3, 4, 5, that would have helped a little bit. Well, what I notice is that all of these numbers are one more than 4, 6, 10, 20. So if you imagine those numbers instead, I think that makes it a lot more clear. Put a 4 here, put a 6 here, put a 10 there. And now maybe you see the relationship between the student's number and the teacher's number. The teacher's number is just twice the number that the student gave. And then to get to the final number, you just add 1. So that's exactly what the rule is. Double the original number n, and then add 1. In other words, if the student gives the number n, the teacher is going to respond with the number 2n plus 1. All right, here's another example. If the student says 2, the teacher says 0. If the student says 4, the teacher says 0. If the student says 7, the teacher says 1. And if the student says 21, the teacher says 1. Well, this might be an example of so easy it's hard. If you're looking for a formula, like we had in the last 2 examples, that's going to make it pretty difficult. But in fact, you don't always have to give a formula. In this case, you could just say the rule is that if the student's number is even, the answer is 0. And if the student's number is odd, the answer is 1. And in all of these examples, other answers are possible, but the ones that we got are probably the simplest ones. Another way to think of a function is a machine. The machine has an input and an output. So in this case, if the number 6 is input, then what comes out is the number 36, and they've written the rule right here. The rule is to square the input. In other words, just take the input and multiply it by itself. The machine works according to the rule. For this function named f, what will happen if the numbers 0, 1, 3, 4, and 6 are input? And it looks like they gave us the answer for one of those. All right. So this is a simple rule. It just says add 3. So that's what we're going to do to all these numbers. It's as simple as that. So if the number 0 is input, then the output will be 3. If the number 1 is input, the output will be 4. So just add 3 to the input. It's as simple as that. 3 plus 3 is 6. 4 plus 3 is 7, like they said right here. and 6 plus 3 is 9. We can write an equation to depict the rule in the previous example. If the input is x, the output is x plus 3. That is, f of x equals x plus 3. So hopefully you've seen function notation before. The first thing that I always say about it is that this is not read f times x. This is f of x. F is the name of the rule. So F never gets a number filled in for it. The only thing that gets a number filled in for it is X. So repeating the example, just done in a different way, F of 0 would be 0 plus 3, which is 3. F of 1 would be 1 plus 3, which is 4, and so on. A function from set A to set B is a correspondence from A to B, in which each element of A is paired with one and only one element of B. So think of the domain as the set of all possible inputs. These are all the numbers that could possibly be put into the function machine. And the range is the set of all numbers that could possibly come out of the function machine. All right, so in this example, they want to know, is this input-output machine a function for any, and the rule is, for any natural number input x, the machine outputs a number that is less than x. This machine would not be a function because remember the rule is each input gets one and only one output. So in this example, if you input the number 10, the machine may output the number 9 because 9 is a number that's less than 10. But then if you input 10 again, the machine may output 3 because 3 is also less than 10. So that is an example of something that is not a function. One input could give you many, many different outputs. Next example, a bicycle manufacturer incurs a daily fixed cost of $1,400 for overhead expenses and a cost of $500 per bike manufactured. First thing they want us to do is find the cost, C of X, of manufacturing X bikes in a day. Well, first of all, since the cost of producing a single bike is $500, the cost of producing X bikes is $500X. And because of the fixed cost of $1,400 per day, so the fixed cost is always the same no matter how many bikes are being made, the total cost, C of X in dollars, of producing X bikes in a single day is C of X equals 500X, so that part depends on the number of bikes that are made, plus $1,400. So that amount is the same every day. It's just a one-time cost of $1,400. Next part of that example, if the manufacturer sells each bike for $700 and the profit or loss in producing and selling X bikes in a day is called P of X, find P of X in terms of X. So the profit would be determined by taking the amount of money that's brought in, which is called the revenue, and subtracting the cost of making that many bikes. So if X bikes are manufactured and sold, the revenue that would come in would be 700X. For example, if they sold 10 bikes, they would bring in $7,000. But then they would have to pay their cost, which would be 500 times 10 is 5,000, plus 1,400 is 6,400. So they would bring in $7,000, but they would have to pay out $6,400. If you leave it in terms of X, it becomes 700X minus the cost, which is 500X plus 1,400, and that simplifies to 200X minus 1,400. And finally, now we can find the break-even point, which is the number of bikes, X, produced and sold, at which break-even occurs. And break-even means no profit, no loss. So that means that the profit would be 0. So we take the expression we just found for profit, we set it equal to 0. That gives us 200x 200x minus 1400 equals 0. If you add 1400 to both sides, you get 200x equals 1400. And then if you divide both sides by 200, you get x equals 7. The manufacturer needs to produce and sell 7 bikes per day to break even. Here's another way to represent a function with an arrow diagram. Arrow diagrams can be used to determine whether a correspondence represents a function. So in this case, the input 0 goes with, you know what, let's look at this one over here because these outputs are not labeled. The input 0 goes with the output 1. The input 1 goes with the output 4. The input 2 also goes with the output 4, and so on. The first example is a function, assuming these 4 things are all different. All right, again, they didn't label them, because each input goes with one and only one output. 0 only goes with this, 1 only goes with this, 2 only goes with this, and 3 only goes with this. However, this thing over here is not a function, and there's only one problem with this, and it has to do with the number 3. The input 3 sometimes will give you an output of 4, but sometimes it will give you an output of 10. So that is not a function. All right, here's another example. Which, if any, of the figures exhibit a function from A to B? If the correspondence is a function from A to B, we'll find the range of the function. First example, this is not a function, right? Because sometimes the input 1 gives you a 2, and sometimes it gives you a 4. That is not a function. This thing here is not a function for a different reason. Remember, the definition of a function is that each input corresponds with one and only one output. The letter B, lowercase b right here, does not correspond with any output. So for that reason, this thing is not a function. However, this thing is a function. There's no rule that says that every element in the set B has to get something sent to it. The only important thing is that each input is matched up with exactly one output. So this is a function, and the range of this function is the set A, B, C. Notice D is left out. All right, continuing with that example. So in this example, maybe the rule is you have these 4 people, and the rule is, you know, I put this person's first name into the machine, and what comes out is their last name. This would be a function, and that's because, generally speaking, a person doesn't have 2 last names. We'll forget about hyphenated names here for a second. However, it is possible for 2 different people to have the same last name. Maybe John and Joan are brother and sister or something. So this is a function, and its range is Brown, Smith, Doe. And this thing over here is also a function. This is actually an example of a one-to-one correspondence. Remember those? The range of this function is 1, 4, 7, 10. All of those elements in set B have something corresponding with them. All right, functions as tables and ordered pairs. The L&B Lawn Service distributes the following fee schedule to their customers. It gives the price for mowing large lots given the number of acres in the lot. These look like pretty good prices, actually. 1 acre is $50, 2 acres is $85, 3 acres is $120, et cetera, et cetera. So this is one way to represent a function. Notice that as soon as you tell me the number of acres, I can give you a unique price for mowing that lot. It's not like sometimes 2 acres is going to be $85 and other times it's going to be $100. The same function can also be represented as a set of ordered pairs. So these are just two different ways of giving you the exact same information. In this example, which of the following sets of ordered pairs represent functions? If a set represents a function, give its domain and range. And if it doesn't represent a function, we'll explain why. Okay. So this is a little different, and I mean, you can feel free to rewrite it as an arrow diagram or as a table. This one here would not be a function because the input 1, remember the first number in the ordered pair is the input, the second number is the output. So we have the input 1 giving us 2 different outputs. So that's no good, that is not a function. However, it looks like in this case, every different input is giving you a different output. Okay, it's not like sometimes 1 is going to 1/2 and other times 1 is going to 1/3. This is a function. Its domain is the numbers 1, 2, 3, 4. Those are all the inputs. And its range is 1/2, 1/3, 1/4, 1/5. Those are all the outputs. Continuing, we have 1, 0, 2, 0, 3, 0, and 4, 4. An example like this will sometimes confuse people. They see the 0 in more than one ordered pair, but actually that's perfectly okay. What's important is that all of these inputs are different. It's not that I have one input going to 2 different outputs. So this is a perfectly good function. And in fact, a shortcut for determining whether a set of ordered pairs is a function is to just look and see, are all of the inputs different? If you see a repeated input, I would suspect that's probably not a function. Okay, just check the output coordinate, but it probably isn't. The domain of this function is 1, 2, 3, 4. Those are all the inputs. And the range is just 0 and 4. There are only 2 different outputs. Now this one might look a little confusing at first. So this would be read the set of all ordered pairs, A comma B, such that A is a natural number and B is equal to 2A. So all this is actually, let me type something for you over here. This is just a different way of writing this set. So the first element in this set would be 1 comma 2. Second element would be 2 comma 4, and then 3 comma 6. It's telling you to make the input any natural number and then make the output twice that number. So that is a perfectly good function. Okay, and I've already lost my mouse. Oh dear. Mouse is always hard to find when, okay, there we go. When I use the text box especially. There we go. Okay. So the domain of this function is the set of all natural numbers, and the range is the set E, which is the set of all even numbers. Okay, let's get rid of this. Graphs are probably the most common known ways of representing functions, the most commonly known way. So here is the L&B lawn service example again. If your lot is 1 acre, they're going to charge you $50. If it's 2 acres, they're going to charge you $85, et cetera, et cetera. Explain why a telephone company would not set rates for telephone calls as depicted on the graph. All right, and there might be a few different reasons. The idea of, you know, paying for a telephone call is kind of foreign to most people. You know, everybody's got their cell phone plan with unlimited minutes. Back in the day, we used to have something called long distance calls. We had pay phones, right? Anyway, there's a bigger problem than that. Look at how much would it cost for a 2-minute phone call. On the one hand, it might cost 50 cents, but on the other hand, it might cost 85 cents. So I have one input, the number 2, going to 2 different outputs, 50 and 85. So for that reason, this is not a function. All right, sequences as functions. Arithmetic, geometric, and other sequences can be thought of as functions whose inputs are natural numbers and whose outputs are the terms of a particular sequence. So we've looked a couple of different times at arithmetic and geometric sequences especially. For example, the arithmetic sequence 2, 4, 6, 8, etc., whose nth term is 2n, can be described as a function from the set n, natural numbers, to the set e, even numbers, using the rule f of n equals 2n, where n is a natural number and f of n stands for the value of the nth term. In this example, if f of n denotes the nth term of a sequence, find f of n in terms of n for each of the following. First, an arithmetic sequence whose first term is 3 and whose common difference is 3. So what would that look like? The first term would be 3. The second term would be 3 plus 3 equals 6. The next term would be 6 plus 3 equals 9. Next term would be 12. So it would go 3, 6, 9, 12, 15. Well, that's a pretty simple function. That would just be f of n equals 3n, where n is a natural number. In the next example, a geometric sequence whose first term is 3 and whose common ratio is 3. So the first term would be 3. The second term would be 3 times 3 equals 9. The next term would be 9 times 3 equals 27. So it would go 3, 9, 27, and then 81. The terms would blow up really fast. And that function would be f of n equals 3 to the power n, where n is a natural number. The sums of sequences as functions. The sum s sub n of n terms, the first n terms specifically, of an arithmetic sequence with first term a sub 1 and nth term a sub n is given by this formula. So the formula is a1 plus an divided by 2, and then multiply that by n. So for example, to find the sum of the first 100 terms of the arithmetic sequence 3, 7, 11, 15, 19, etc., first we have to notice that the common difference is 4, and then we use the formula that we learned way back in chapter 1 to calculate the 100th term of the sequence. So that would be 3 plus 100 minus 1 times 4. That comes out to 399. And then finally, we use this new formula, n times a sub 1 plus a sub n divided by 2. That comes out to 20,100. Might be nice to compare that answer to the way we did this problem back in chapter 1. Remember where we wrote out the sum and called it S, and then we wrote it out again in the opposite order, and we added those two together, and we got 2S equals, okay? Look back in your notes, you'll see you get the same answer. The sum of the first n terms of a geometric sequence whose first term is a sub 1 and whose common ratio is r is given by this formula. Now don't freak out about all this. They're just saying that there are two different ways to write it, which are both correct. So you could either write a sub 1 times 1 minus r to the n divided by 1 minus r, or you would get exactly the same thing if you wrote it as a sub 1 times r to the n minus 1 divided by r minus 1. So in this example, we'll find the sum of the first 10 terms of the geometric sequence that starts with 3, -3/2, 3/4, -3/8. What's nice about geometric sequences is that you do not need the 10th term. All you need is the first term and the common ratio. So the common ratio, let's see, I think there is, yeah, there's a little typo here. Okay, this is supposed to be a 3. Remember, the easiest way to get the common ratio is to just divide the second term by the first term. Okay, so -3/2 divided by 3 comes out to -1/2. And we know the first term is 3. Uh-oh. Okay, so here's what our formula gives us. A sub 1 is 3. Up here we have 1 minus r to the n, which becomes 1 minus the 10th power of -1/2. And we divide that by 1 minus r, which is 1 minus -1/2. That comes out to 1,023 divided by 512, which is equal to 1.998. So the first 10 terms of this sequence add up to 1.998. All right, and finally we have composition of functions. So this is one function followed by another function. In this example, they're putting a 2 in the top machine. And what this machine does is it adds 4 to the input. So what's going to come out of there is the number 6. That number 6 is then going to get put into a second machine. The rule for the second machine is 2x, so just double the input. And what comes out is the number 12. So this illustrates composition of functions. The idea of the composition of two functions, it gives you one new function where the input is 2 and the output is 12. It kind of cuts out the middleman here. Notice that the range of f, which is the set of all possible outputs for the first machine, is the same as the domain of G, which is the set of all inputs for the second machine. Those two things are exactly the same. All right, so if f of x is 2x plus 3 and g of x is x minus 3, let's find each of the following. First, f circle g of 3. This is how we write function composition. And what that means, let me just put this for you right here. This f circle g of x means f of g of x. So hopefully this will make a little more sense when we look at an example. So f circle g of 3 means f of g of 3. So what does function g do? It takes a number and subtracts 3. So that's what we're going to do right here. So in other words, we're just turning this into this. Those two things mean exactly the same thing. 3 minus 3 is 0. And then what function f does is it takes a number, doubles it, and adds 3. So that's what we're going to do to the number 0. And what we end up with at the end is the number 3. So we started with the number 3, we put it into the G machine and got a 0. And then we put the 0 into the F machine and we got back a 3. All right, now let's look at G circle F of 3. So the only difference is that now we're going to take the functions in the reverse order. So just like f circle g of x meant f of g of x, g circle f of x means g of f of x. Okay. And I gotta find my mouse again. Okay, here we go. Got it. Okay, so G circle f of 3 means G of f of 3. Remember that what the F machine does is it takes a number, doubles it, and then adds 3. So 2 times 3 is 6. 6 plus 3 is 9. And so now we're going to put the number 9 into the G machine. The G machine just takes the input and subtracts 3, so that's going to give us a 6. All right, and then the last thing that we're going to look at is writing those functions in terms of x. So my Math C students, intermediate algebra, they always get a little confused by this at first. Takes a little bit of practice. First, we have f circle g of x. Remember that means f of g of x. So what does function f do? It takes the input, which is now g of x. It multiplies it by 2 and then adds 3. So now all we have to do is just replace that g of x with what g of x stands for. It stands for x minus 3. So that's going to look like this. And now we're just going to simplify that expression. We're going to get 2x minus 6 plus 3, which is 2x minus 3. So I like to think of composition of functions as direct flights. Instead of having to get on flight G and then change planes and get on flight F, you can just take the direct flight. The direct flight would take you from your original input directly to the number 2x minus 3. And then if you went the other way around, G circle f of x, what that would look like is G of f of x. And what does function g do? It takes a number and subtracts 3. All right, now we're going to replace f of x with what f of x's rule is. And that rule is 2x plus 3. And when we simplify this expression, we just get 2x. So the direct flight, start on flight F and then hop off and get on flight G. It would take you from your original input to 2 times that input. And that is going to do it for section 8.3. We only have one section left, and we will do that next time. See you then.